Alright, we're going to take a minute here and go over what we did yesterday. A quick review. We're going to go over the answers to the 4 elements that I asked you to analyze for protons, neutrons, and electrons. And I want to talk to you about something called a nuclear symbol before we get into the average atomic mass calculations. So remember, on the periodic table, every element has a box. Okay, all 118 known elements has its own box. That box consists of the element name, the atomic number, which is the number of protons, its elemental symbol, its average mass, which we're going to look at how we calculate today. If we round this to the closest whole number, then we end up with the number of protons and neutrons together in the nucleus. So we can use the rounded mass minus the atomic number to figure out the number of neutrons in an element. We can also assume that elements are neutral for right now, that atoms are neutral, so the atomic number tells us the number of protons, and thus if it's neutral, the protons and the electrons are going to be the same. So the atomic number gives us protons, we can find electrons from protons, and then mass number minus atomic number gives us our neutrons. Let's take a look at a couple examples that we went over yesterday. Neon. We know that it's neon by the symbol. We can look over on our periodic table right there. You can see neon. Atomic number 10, mass of around 20 if we round it. And we end up with 10 protons. Number of protons equals the atomic number. Electrons and protons are equal as long as the atom is neutral. And we're going to assume everything's neutral for right now. So 10 protons, 10 electrons, and then if we take the mass number, which is the rounded average mass of 20, minus the atomic number of 10, we get 10 for our neutrons. We can write all of this information in what we call the nuclear symbol by placing the element symbol at what we would picture as the center of a clock face. And then in the top left quadrant, we put the mass number. In the bottom left quadrant, we put the atomic number. Let's do the same thing for arsenic. Arsenic had 33 and 74.9215. 33 is our atomic number. 33 is our atomic number, so that's how many protons we have. It's a neutral atom, so protons is equal to electrons, so that'll also be 33. And then we take the mass number minus the atomic number to get 42 neutrons. The arsenic nuclear symbol, the nuclear symbol, would be arsenic 75 top left, 33 bottom left. You can pause the video now and take a look at silver and xenon. Check your work against theirs, make sure you have the right numbers in the nuclear symbol. What we want to move on to now, once you've checked your work, is we want to talk about isotopes. Now isotopes are atoms of the same element that have different masses. They're the same element because they have the same number of protons. The thing that causes the mass to change is that they have a different number of neutrons. Atoms' masses are due to the number of protons and neutrons together. So if you're ever asked to calculate the mass of an atom, you simply take the number of protons plus the number of neutrons, and that would be the mass of an atom. And that would be in a unit called an AMU, which is an atomic mass unit. Okay? Now, the average mass that we find on our periodic table, the average masses, is a weighted average calculation that takes into account the different isotopes that exist for an element and their percent abundance. The percent abundance is, as a percent, how much of a sample is a certain isotope, an atom of that element with a distinct number of neutrons. All atoms are isotopes, so keep that in mind. Every single atom is an isotope. The number of protons determines which element it is. The number of protons and neutrons together determines which version or isotope form it is in. The calculation we're going to use to determine the average atomic mass for the elements on the table is we're going to take the mass of each isotope times the percent abundance. And we're going to write the percentages as decimals. Okay, we're going to write the percentages as decimals. So 95% would be written as 0.95. And then once we do that calculation for every isotope that we have, some have 2, some have 10 isotopes. We do mass times percent abundance, and then we find the sum. We add all of those up. Okay? Make sure you convert your percentages to decimals when you plug them in. And then don't forget the atomic mass unit is the unit for our mass. Protons plus neutrons equals the mass in AMU. And AMU is equal to 1/12 the mass of a carbon-12 atom. That's an atom of carbon with 12 particles in its nucleus. 6 of them are protons, 6 of them are neutrons. The mass of a proton or a neutron is roughly 1 AMU. The mass of an electron is irrelevant because they are so insanely small that they don't even register. So here's what we're going to do now. We're going to go through a practice calculation for lead, and we're going to use this equation and apply it to the lead atom and then, or the lead element, and then we're going to come back and compare that to our lead number on the periodic table, which is 207.20. So here is our sample problem. So if we're asked to find the mass of lead as an element, what is the average mass of lead as an element? We're going to use our average mass calculation. We're going to use the percent abundance times the mass of each isotope. We're going to multiply those together, and then we're going to add all of those up. So here's what we know so far. We know the average mass of lead has an isotopic abundance. There's 1.4% is lead with a mass of 204. We know that 24.1% of the sample has a mass of 206. 52.4% of the sample has a mass of 208. And the rest, 22.1%, has a mass of 207. So if we look at all these values right here, how do we plug these numbers of this information, how does that plug into the average mass calculation? So the first thing we're going to do is we're going to take our first set of data. 1.4% is going to be 0.014. 0.014 times the mass of 204. If we plug that in and we do that math, we get 2.856 AMUs. Then we're going to take the next set of data, 24.1% at 206. So that means 24.1% of the sample has a mass of 206 AMUs. 0.241, we're going to change our percentage to a decimal, 0.241 times 206 AMUs. That product would give us 49.646. The next set of data we have is 52.4, which would be 0.524, has a mass of 208 AMUs. That product is 108.992. And then if we do our last piece of data here, 22.1% would be 0.221 with a mass of 207 AMUs. The product of that is 45.747. So we took the mass times the percent for each isotope, the mass times the percent. So these are your masses: 204 AMU, 206 AMU, 208 AMU, 207 AMU. We plugged those in, and then we multiplied each of those by their percentages as decimals. We took those, and now we're going to get a massive product, 207.241
207.24 is what we get when we round it to 2 decimal places. You can see that our average from the periodic table is 207.20. That's a really close, good value for that. You can do this anytime. So when you have a set of data like this one, silicon with a mass of 28, so that would be the Si 2814, that would be its nuclear symbol. This one would be Si 2914, this one would be Si 3014. And then you have the percent abundances. You would take the percent abundance times the mass, percent abundance times the mass, percent abundance times the mass, and then add those all together. Once you get that, you'll get your mass from the table. And whether you use the big long numbers for the masses or you use the shorter numbers for the masses, you end up with 2/100th difference. So using the mass numbers is sufficient for this. There's 2 more practice problems that are attached. I'd like you to finish those. They look, you'll see them whenever you get down to the bottom of this notes page. If you have any questions, we will go over these first thing tomorrow as we get ready for, or actually on Thursday, we'll go over these 2 practice problems as part of our review for the test.